Hey everyone, we are here again with some more live office hours with Chegg. Once again, Chegg is bringing you office hours in a multitude of different topics all semester long. If you want to go to that QR code on the top left, you can see all of the subjects that Chegg is doing office hours for. I myself am partnering with Chegg to bring you Organic Chemistry 1 office hours throughout the semester. So we are doing these every Tuesday at 5 p.m. PST, Pacific time. So we are here, we're live, and feel free to ask Organic Chemistry 1 related questions in the chat. I have some questions that I am going to be going over because I'm sort of trying to map roughly an Organic Chemistry 1 syllabus as we move through the semester. But if you have questions that are at the very least Organic Chemistry 1 questions, even if they're not directly related to what I'm talking about, feel free to ask away. Every week we do get a lot of people talking about things that have nothing to do with OChem 1. So if we could please refrain as much as possible from the unrelated stuff, that would be great. We're talking about Organic Chemistry 1. So let's go ahead and dive into this stuff here. Let me get over to my document. So we have been going through, last week we continued with SN1, SN2, E1, E2, and then we started introducing some addition reactions. Addition reactions are a very big unit in Organic Chemistry 1 because there's a lot of different addition reactions that we definitely need to know. And addition reactions operate on alkene or alkyne substrates. So we'll look at a lot of stuff with alkenes. Remember, pi bonds have to be involved on the substrate in an addition reaction. So we're going to go through a bunch of addition reactions today, and we'll see where we get. So this first one here says draw the product of the following transformation. We have this cycloalkene. We've got these two methyl groups right there, and then we're reacting with D2 over a catalytic palladium surface. And so what is D, right? We know that's not on the periodic table. What is D? Well, D stands for deuterium, which is an isotope of hydrogen. So it's a heavier version of hydrogen. It's got a neutron in there. And so D2, right? It's basically H2, but we're looking at deuterons instead of protium would be the more common isotope with just a proton in the nucleus. So this is the same as just regular catalytic hydrogenation. It's a heterogeneous catalysis. Remember, we've got a solid support that is the catalytic surface, and then the molecules are whether they're in solution or in the gas phase, they are approaching that solid catalytic support. They're receiving the in this case the deuterons, the hydrogen atoms, but they're deuterium, and they are going to add to this double bond. And they will do so in syn fashion. So syn means it's a stereochemistry term. It means that they are adding to the same side of the double bond. Remember, we're going from sp2 centers to sp3 centers. So these are trigonal planar. This part of the molecule is flat. And so when it approaches, we'll get those two deuteriums on there, and they'll be added to the same side. And then there'll be sp3 centers there. So if it is syn, what that means is that they must be on the same side on the product. So if there is a syn addition, they will be cis to one another on the product. And so let's just say that ends up looking like this. So the methyl groups, so here is D, here is the other D. We could have drawn them, we could have drawn deuterium on the wedges and the methyls on the dashes. That would actually be the exact same molecule. So the point is that this is syn addition. So syn refers to the stereochemistry of a reaction. So syn addition means they're added to the same side of the molecule. That means that these methyls end up cis to one another. Cis is terminology that refers to a molecule. Syn and anti refer to a reaction. Cis and trans refer to a molecule, the spatial orientation of groups on a molecule. So these methyls end up cis because the deuterium, the deuterons end up cis. So there's your hydrogenated product. The pi bond is gone. and that's what we get. We get a cycloalkane. Let's see if we had any good questions here. What is the most important math formulas in Organic Chemistry 1? There's not too much math, I'll be honest. Organic Chemistry 1, we are just going over structures and mechanisms. Mechanisms is what we do. There's a little bit of math. I mean, I guess off the top of my head, we talk about the Gibbs free energy equation. In order to determine the spontaneity, the relative degrees of spontaneity of competing reactions. So we look at that when we want to talk about like elimination or substitution, which one is going to be more favorable. Hotter temperatures make entropic favorability a greater factor in determining spontaneity. So that would be one. But honestly, that's kind of the cool thing about Organic Chemistry 1. There's not a lot of math, right? I mean, some people find this harder than math, right? Just this really weird abstract world of organic molecules, and you have to learn this new set of rules, this new set of logic about electron excess seeks electron deficiency, and you got to figure out what is going to happen. So yeah. Okay, Ryuchiro asked, when will you talk about HNMR to structure? So, okay, I think you've asked that more than once, and so I will try to remember, because that it is true that rather than just waiting and doing a whole week on spectroscopy, maybe we can throw in one spectroscopy question each week. That's actually not a bad idea. So thank you for that. Next week, I will try to remember to throw a spectroscopy question in there. Let's see. Preston says, can you review stereochemistry? Dashes and wedges are confusing me. So as we go, there will be stereochemistry to talk about. For example, this one, this was a stereo-specific reaction. It was a syn addition, which is why the methyls are cis to each other on the wedges, which means they're coming towards us. The wedges are coming towards us. They're closer to us than the screen. The dashes are pointing away from us. They're farther away from us than the screen. So there's a little bit of spatial reasoning. You kind of have to be able to visualize that. This is not flat. We use wedges and dashes to depict a three-dimensional molecule on a two-dimensional surface. So over time, that becomes intuitive. When I look at this, I see the 3D, and that just takes some practice. Let's see. Chukwu asks, does the stability of the leaving group play a role in these reactions? So there is not a leaving group in an addition reaction. In an addition reaction, the pi bond is reacting, and two groups will be added to those two carbons that were participating in the double bond. And then Chukwu also asks, are these Markovnikov selective reactions? So great question. Several times today, and in fact, in the next question, we will be talking about Markovnikov, anti-Markovnikov regio specificity. The Toadster asks, isn't there a lot of dimensional analysis in Chem 1? In Gen Chem 1, yes, absolutely, there is a lot. In Organic, not really, because we're not really dealing with units of measurement. I mean, you could, like, there definitely could be a question made on purpose to have dimensional analysis, but mainly what you do in OChem 1 is just a lot of reactions. What are the products going to be? What were the reactants? What are the reaction conditions? Draw the mechanism, right? That kind of stuff. So there's not really a lot of, not even really a lot of measurement in general. Let's see. Doncom asks, how do you chemical reactions and know whether it would create something, cancel something, or destroy something? I'm not really sure what that means. So we're not really going to create or destroy anything. A chemical reaction is simply where bonds break and form, right? Chemical bonds are breaking and forming. So the conservation of mass applies. Right, all of the atoms that were there at the start are still there at the end. They've just rearranged their combinations. That is the definition of a chemical reaction. Princess Akoto asks the difference between alkene and alkyne. So an alkene has one double bond, one carbon-carbon double bond. An alkyne has at least one carbon-carbon triple bond. So we will see many alkenes and also a couple of alkynes today. Jome asks, do we get two products in this reaction? No, we don't in this one because this is symmetrical. So if you were to draw the deuterons on the wedges and the methyls on the dashes, it would actually be the same molecule. So we just get one answer here. And that's it. Preston asks, does it matter if it is R or S? Or only if the nomenclature of the yeah. So if you were to name it, you could. Well, here we would just say cis, cis 1,2 dimethyl cyclopentane. Yeah. So no, we're not going to worry about nomenclature today. Okay, moving on to provide an example of stereospecificity and an example of regiospecificity. So for stereospecificity, we're talking about the potentiality of generating multiple stereoisomers, but there's a specificity. We only go one way and not the other. So for example, as we just saw, right, if we have this and if we have this cycloalkene and we're going to do an addition reaction, there are two possibilities, right? These could end up, let me draw that down here a little bit. We could either get syn addition, and the groups will end up cis to each other. So syn gives us cis, or we could get them, it could be anti-addition, which would yield trans. We would get the groups trans to one another. So that is an example of stereospecificity. This gives us the option of stereospecificity. For example, the reaction that we just looked at was a syn addition. We exclusively got syn addition, meaning that the deuterons and the methyls ended up cis, right? The two methyls end up cis to one another. The deuterons ended up cis to one another because that was a stereospecific reaction. We did not get the other possible stereoisomer. We did not get the methyls trans to one another or the deuterons trans to one another. And now every stereospecific reaction, the stereospecificity is occurring for a different reason. In this case, it's because it's heterogeneous catalysis. If the substrate is being lowered onto the surface containing the deuterons, there is no way for the deuterons to attach to the molecule other than from the same side because they're attached to this solid support. Other stereospecific reactions are stereospecific for other reasons. That would be the reason for that one. But it is a syn addition. That's all it means, is that they're added to the same side, and that yields the cis isomer. And so that is stereospecificity. You have the potentiality for multiple stereoisomers, but you get specifically one stereoisomer. Then regiospecificity, that is when you could have potentially different structural isomers, but you preferentially get one. So here, let's do another addition reaction. And let's say we can get A there and B there, or we can get B here and A here. And so these are different structural isomers. These are not stereoisomers. Stereoisomers only differ in the way, all the connectivity is the same, but the groups differ in the way they're oriented in three-dimensional space. This is not that. These are structural isomers, right? A is connected to the secondary carbon, but over here it's connected to the primary carbon. And then B was on the primary and now it's on the secondary. These are different structural isomers. So regiospecificity is when we get one potential structural isomer over another. And in the context of addition reactions, that's going to be talking about Markovnikov additions versus anti-Markovnikov additions. And I have several examples of those that we're going to get to, so I will highlight this again. But this is just, it's very important to know what stereospecificity means and what regiospecificity mean. And also, by the way, stereoselectivity and regioselectivity and how they're not the same thing. Stereospecificity means you only, or specificity in general means you get only one and not the other. Selectivity means you get a distribution, but there's a statistically significant, right there, it goes one way more than the other. So let's say you get 80-20, right? If you get 80% the Zaitsev product and 20% the Hoffman product when you're doing elimination, that is an example of regioselectivity, because you do get both, but the one is dominant in the product mixture. It's selective. So that's regioselectivity. Regiospecificity is different. When we get a Markovnikov hydrohalogenation, we're only getting Markovnikov. It's specific. We don't get the other one. So that's what those words mean. Okay, let's see. Chuku asks, can you explain the difference between electrophilic addition reactions and nucleophilic addition reactions? So the substrate for the addition reaction is an alkene or an alkyne, right? We need a pi bond. We need one or more pi bonds on the substrate. When it's electrophilic addition, then the pi bond is acting as the nucleophile and it is attacking an electrophile. And most of the addition reactions that we're going to look at here, that's what we're talking about. We're saying that the pi bond is acting as the electron excess and it is attacking some electrophile, something with electron deficiency. If we were talking about something nucleophilic, that would mean that a nucleophile is attacking the pi bond because it can then shift and do something else. So that'll be more when we talk about like Michael additions and stuff like that. There's a lot of other stuff where we can see nucleophiles attacking pi bonds. So we'll see that later. Okay. All right, let's go to the next one. 3, if the following compound reacts with hydrogen gas, if the following compound reacts with hydrogen gas over platinum metal, draw the products that result and state which is more energetically favorable. So we're doing H2 over PT, palladium, platinum. There are multiple catalytic surfaces that will promote this. So once again, 2 hydrogen atoms are going to, this is a syn addition because it's heterogeneous catalysis. It's a syn addition. So the 2 hydrogen atoms are going to add to the same side of the substrate. So whatever's already there, in this case, a methyl and an implied hydrogen, will also get pushed to the same side, the other side. So what results? Okay, we're going to lose this pi bond. And then we have 2 sp3 centers with methyl groups. So we're either going to get those cis to one another, or we're going to get them trans to one another, right? And honestly, there are 2 possible isomers here, right? These are not the same. These are enantiomers. This would be a diastereomer of the other 2. So, but then the question asks, which is more energetically favorable? So what does that mean? Well, we have a cyclohexane derivative, and if we're talking about stability, we have to look at this in appropriate conformation. We have to draw some chairs. So let's draw a chair for the cis isomer. There's only one cis isomer. So let's say we're going, okay, let's put this methyl is up, so let's put that up axial. And then we go 2 clockwise, boom, boom. We have another one up, and so that's axial. So that's one of the chairs. Now let's do the chair flip. So we got to draw the other chair. And so now, remember, this is the leftmost carbon. So there on the leftmost carbon, there's a methyl pointed up. And now still on the leftmost carbon, there's a methyl pointed up. It just happens to be that on this chair, the up is axial, and on this chair, the up is equatorial. Necessarily, that's just how those bonds are oriented at that carbon. Then once again, we go 2 clockwise, and we have another methyl up. And again, on this carbon, that happens to be the equatorial position on that carbon. So here we have 2 axial, and here we have 2 equatorial. We know that the equatorial position is the more favorable, more energetically favorable position for each carbon in the chair. And so the best situation we could have is 2 equatorial methyls. So definitely, we don't even have to look at the trans isomers, because we know that for the trans isomers, if one is up and one is down, then in one chair we'll have an axial methyl and an equatorial methyl. And then when we flip it, they'll switch. The one that was axial will be equatorial. The one that was equatorial will be axial. So this is definitely the best one. And let me do this in red too. This is the most energetically favorable situation. And so this equilibrium will not be even, right? It will spend more time in the diequatorial conformation. That's the best situation for it to be. So there's a higher activation energy associated with it flipping over the diaxial than flipping back. So just kinetically, it will flip. It'll just spend more time. If you took a snapshot of the trillions upon quadrillions of these molecules in a sample of this substance, a dramatically greater proportion of them would look like the diequatorial conformation at any given time. Some of them would be diaxial, but it would be the minority. More of them would be in the diequatorial conformation. So we're combining an addition reaction with some stuff about conformational analysis, chair structures for cyclohexane derivatives. So that is that one. Let me see if I missed anything. Lunar 313 says, what is delta G? Delta G is the change in Gibbs free energy. It is the parameter that determines the spontaneity of a reaction, whether it is spontaneous and will simply occur. I think I wrote it up here. Delta G equals delta H minus T delta S. So delta G is the change in Gibbs free energy. If this parameter is negative, then a transformation is spontaneous and will simply occur. If it is positive, it is non-spontaneous and will not occur spontaneously without energy input. Delta H is change in enthalpy, essentially change in energy or heat exchange if we're looking at constant pressure. And then T is temperature in Kelvin, need the absolute temperature scale. And delta S is change in entropy, essentially the change in the dispersal of matter and energy in the system. And so this is probably the most important aspect of thermodynamics in organic chemistry, because every reaction has a change in enthalpy and a change in entropy and is done at a particular temperature. And then there are often competing reactions. And so we want to see, is substitution more likely? Is elimination more likely? Is this particular elimination product more likely, or this other elimination product, right? We can have Zaitsev versus Hoffman elimination products. One of them is going to be thermodynamically driven. The other is kinetically driven. So that is a concept we're going to see a lot. So definitely every organic chemistry has to know this equation. There are very few equations you have to know. This would be one of them. Let's see. Jenna asks, can you explain electrocyclic reactions and how to determine configuration of methyl groups in disrotatory and conrotatory fashion? Yeah, there's a whole set of rules for that. I'll have to prepare that for another time. I think that's all the Baldwin's rules stuff. Electrocyclic, I think maybe when pretty soon we can go from addition reactions to like ozonolysis and Diels-Alder and all that stuff. And so I'll throw in some other non-Diels-Alder electrocyclic stuff when we talk about that. Yeah, Chukwu asks, can dienes participate in these reactions? Absolutely, of course they can. And if you have dienes where the pi bonds are isolated, then each pi bond will react in a normal addition reaction, and it'll just be right. Either of them could react. If you have a conjugated diene, right, where you're alternating double bond, single bond, double bond, then resonance becomes a factor, and there's some interesting stuff that can happen mechanistically. Since today we're just introducing a lot of addition reactions, I'll throw in some of the addition reactions on conjugated polyunsaturated systems next week. And yeah. MS asks, can you do aromatic substitution? So like electrophilic aromatic substitution, that's a whole unit unto itself. And I obviously will get to that because that's a super important topic. So I will get there. Chiku asks, what is the importance of conjugated dienes in addition reactions? So you can have a conjugated diene and it will react. I promise next week I'll throw one or two in there. It's just that if there are addition reactions that have intermediates like dihalogenation has like the bromonium. If you do dibromination, there's the bromonium intermediate. The other pi bond could then react. Right there, it's just you can have there's a wider variety of structural products that can result because of the position of that other pi bond. So it just makes the product mixture more complicated. So I'll show that next time. Let's see. Okay, number 4. So now we're going to fire through a bunch of these addition reactions. So there's a pro and a con about addition reactions. The con is that there is some memorization. So with a lot of and it's not just addition reactions, it's just that addition reactions is a very large class of reactions. John asked, when are you doing these office hour sessions? We're doing these every Tuesday at 5 p.m. Pacific, which is right now. So yeah, every Tuesday. So as I was saying, it's a large class of reactions, and we have to be able to look at a set of reaction conditions and know immediately what transformation they promote. And so there is some memorization there. So for example, here, we have to know that these reaction conditions denote hydroboration oxidation, which is syn anti-Markovnikov hydration. So that is memorization. And I recommend flashcards, whatever you need to do, but we have to look at this and go, this is syn, it is syn anti-Markovnikov hydration. That is memorization, but that is the only thing that is memorization. If you successfully memorize that, the rest is relatively trivial because all we're doing is applying our knowledge of what those words mean to whatever substrate we're given. So what do these words mean? Hydration means we are adding a water molecule in the form of a hydrogen and a hydroxyl. So the two bonds, the two carbons that are participating in the pi bond, one of them is going to get a hydrogen, the other is going to get a hydroxyl. Now, which one gets which and from which direction? These are additional questions that we have to know the answers to. All hydration tells us is that one carbon gets a hydrogen, one carbon gets a hydroxyl. That's what hydration tells us. Anti-Markovnikov tells us the regiochemistry of the addition reaction. So what that tells us is that the more relevant group that's being added, in this case the hydroxyl, will go to the less substituted carbon that was participating in the pi bond. That's what anti-Markovnikov means. If we're doing hydrohalogenation, if we're doing hydration, whatever it is, if the two groups being added are different, then the more significant one is being added to the less substituted carbon in the pi bond. And then syn tells us the stereochemistry. The two groups are being added to the same side of the molecule as opposed to one being added from this side and the other being added from this side. So now let's take everything we just said and figure out the answer to this question. So hydration, one of these carbons gets an H, one of these gets an OH. Anti-Markovnikov tells us that OH is going to go to the less substituted carbon, and H is going to go to the more substituted carbon. That's what anti-Markovnikov means. If it was Markovnikov, OH would go to the more substituted, right? This one is more substituted because it's tertiary. It's connected to 1, 2, 3 carbons. This one is secondary. It's connected to 1, 2 carbons, only 2. 2 is less than 3, less substituted. So OH is going to the less substituted, and then syn means they're being added to the same side. So that's all the information we need to be able to draw the product. We've got this 7-membered ring, 1, 2, 3, 4, 5, 6, 7. And we have, so let's say we added them to the top. We're looking at this top down. Let's say we went top, added to the top. So this propyl group will get pushed down onto the dash. And then we have the OH on the wedge over here. And we have the hydrogen over here. Plus enantiomer, right? That will, so this is even though it is stereospecific in the sense that the two groups are being added to the same side, we will still get a mixture of stereoisomers because we're creating. The carbons that are participating in the pi bond are sp2. That's a flat portion of the molecule. So the two groups can approach from the same side on this side, or they can approach from the same side on this side, right? So even though it's stereospecific, you do get a mixture of stereoisomers as a product. So once again, hydration told us H plus OH. Anti-Markovnikov told us OH onto this carbon and not that one. And then syn told us they add from the same side of the molecule. So they end up cis to one another on the product. That's also a very important thing. People associate syn with cis. And so it's very tempting for students to think that the hydroxyl and the propyl will end up cis to one another, but that's not the case. Syn refers to the groups that are being added. The groups that are being added are the hydrogen and the hydroxyl. So the hydrogen and the hydroxyl end up cis to one another on the product. Those are being added to the same side. So there is the answer. So again, we have to look at this, and we do have to memorize this is syn anti-Markovnikov hydration. From there, we just apply what those words mean to the specific substrate that we are given. And we know that that's going to be the answer. So let's see if we missed anything. Ryan got it correct. Yeah, that is true. But don't forget the anti-Markovnikov regio specificity. Looks like we got some people that should get blocked here. Let's see. Yep. Okay, Jonathan Ramos, can you teach me saponification? That's a little more. That'll be probably the very last unit of OChem 1. Honestly, it's really the biomolecule stuff is really more OChem 2 content. At the end of OChem 2, there's a lot on amino acids and polypeptides and other various biomolecules. But maybe at the end of the semester, I'll throw in some of that. Okay, so 5, draw the product of the following transformation. So this is another flashcard thing here. We have to look at this and know that we are doing Markovnikov hydration. So if this is Markovnikov hydration, if it is a hydration, we are adding H and OH. And if it is Markovnikov, it means, Joam asked, quickly explain anti-Markovnikov one more time. So yeah, that's what I'm saying right now. So Markovnikov means the more significant group is being added to the more substituted carbon. So that means that OH is going there and H is going there. So that's what Markovnikov means, right? This is a secondary carbon. It's connected to 2 other carbons. This is a primary carbon. It's connected to 1 other carbon. So the secondary carbon is more substituted. So the OH is going there and the H is going to the other one. That's Markovnikov. If we had conditions that were promoting anti-Markovnikov hydration, then the OH would go to the less substituted. It would go to the terminal carbon and the H would go to the secondary one. So this is it. That's all we need to know. In order to answer this, we're going to go ahead and add those. And so the thing that we need to understand here, though, is that if we are doing an addition reaction on an alkyne, then and I'll go ahead and, well, the H is implied. I'll go. There are 2 pi bonds in the alkyne, right? And only one of them is reacting. We have an addition reaction. So one of those pi bonds is reacting to add OH and H. And so one is left over. So when we do an addition reaction on an alkyne, we get an alkene. When we do an addition reaction on an alkene, we get an alkane, or a derivative of an alkane. When we do it on an alkyne, only one of the pi bonds goes away. So one of them is left. So what is this? We have an enol. And the important thing to understand about enols is this. They are going to undergo tautomerization typically. There are actually counterexamples where the enol tautomer is preferred. But here we're going to do this. So this pi bond is going to grab that proton, and then this is going to snap shut and make the carbonyl. And so the keto tautomer, is going to be preferred thermodynamically. And actually, let me erase this because this is an equilibrium. But this is preferred. The keto tautomer is preferred, and that's for reasons of thermodynamics. If you just look at a table of bond enthalpies, we're just comparing OH, CO, and CC double bond to CH and CO double bond. And carbonyl is very thermodynamically favorable. The more bonds you have between the polar bonds are more energetically favorable. There's something about the polarization there, oxygen bound to carbon, that brings the system to a lower energy. And so the keto tautomer is typically preferred thermodynamically. Again, there are counterexamples, but in this case, that is it. Okay, let's see. Martian asks, please explain SN1 and SN2 reaction. So we kind of covered that quite a lot the last 2 weeks. I'll try to keep throwing in one or two of those as we move along, but in most curricula, we would be past that by now. But you can feel free to go to my, if you go to my channel and you click on the live tab, all of my previous office hours with Chag are there, where I did talk about those for a long time. So go ahead and check those out. Daniel asks, would EZ or cis trans be applicable here? And so in this case, it actually would not, because on the pi bond here, one side has two hydrogens, identical hydrogens. So there's no E or Z to talk about. Chuku asks, this is the keto-enol tautomerization. That is absolutely correct. This equilibrium, these are two tautomers in equilibrium with one another, and the process of going from one to the other is called tautomerization. And again, the keto tautomer is preferred in this case. The cases in which the enol tautomer is preferred are ones in which the enol tautomer is aromatic, things like that. That would be an example where the enol is preferred. Jonathan asks, what specific unit of is this? This is a very large, in any Organichem 1 class, there's a very large unit on addition reactions, those in which we have an alkene or an alkyne substrate, and groups are being added to the two carbons in participating in the pi bond. And so this is usually, at least the way I taught it, and I think a lot of other people teach it, the unit that comes after SN1, SN2, E1, E2, introducing those very first, very simple mechanisms. So that's what that is. Okay, let's check out another one. So draw the product of following transformation. What are these conditions? Here's another flashcard here. We have to know that this is anti-Markovnikov hydrohalogenation. So HBr tells us that it's hydrohalogenation, and then peroxides are a giveaway for anti-Markovnikov. There are multiple mechanisms that are anti-Markovnikov because of the presence of peroxides. And so ROOR, peroxide, refers to a functional group in which we have two oxygen atoms covalently bound to each other. And that oxygen-oxygen bond is quite weak and will tend to undergo homolysis readily. And so homolysis means that instead of heterolysis, where bonds break with the two electrons in the bond going to one atom and not the other, here we're talking about individual electrons, one each going to each of the oxygen atoms. So these are typically radical mechanisms. We're not going to go over the mechanism right now. Maybe another week we'll rigorously go over the mechanism. But what we need to know in this case, all we're doing is drawing the product. It's a hydrohalogenation, which means if it's HBr, that means we're adding an H and we're adding a bromine. We're adding a hydrogen and we're adding a bromine. And because it is anti-Markovnikov, that means the bromine is going to go there and the hydrogen is going to go there. The bromine is going to go to the less substituted side. That's what anti-Markovnikov means. The bromine, in this case, will go to the less substituted side. So we get boom, 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 boom. the bromine ends up here and not here. The hydrogen that was added ended up here. It is implied, so we don't have to write it. But we know that the bromine is going to the less substituted carbon. That is your anti-Markovnikov hydrohalogenation. Okay. Okay, that's it. So number 7, again, draw the product of the following transformation. So let's look at an alkyne. This actually is not an addition reaction, but when we're looking at alkene and alkyne substrates, sometimes we're going to throw in some other reaction types. So what is going to happen here? NaNH2. What is that? Okay, so first of all, we definitely have to be able to remember, we have to be able to recognize when things are ionic, right? This is Na plus NH2 minus, right? Now, and we can always tell when you have a metal from one of the first two groups, the alkali metals or the alkaline earth metals, those are almost always counter ions to something that's going to act as a base or nucleophile. So NH2 minus, what's that? Is that basic? Well, actually, it very much, it's extremely basic, right? NH2 minus is so basic that its conjugate acid, NH3, ammonia, is a base, right? It's extremely basic. It's so basic, in fact, that it can deprotonate terminal alkynes. So alkynes are not especially acidic, right? The pK, I mean, they're more acidic than alkenes and alkynes. They're more acidic than alkenes and alkanes. Alkanes have a pK around 50. Alkenes have a pK around 40, not acidic at all. Alkynes, this is about pKa, I think around 25. So it's still a billion times less acidic than water, right? We're talking about 9 orders of magnitude, but it is just acidic enough that an exceptionally strong base like NH2 minus is going to go ahead and get that proton and leave that negative charge on that terminal carbon. So we have now an alkynyl nucleophile. So here, let's do that. Boom, boom. We have an alkynyl nucleophile. And now what is adding after that? We have H3Ci. We have methyl iodide. Actually, let me go ahead and explicitly draw out that bond. And so now these alkynyl anions are excellent SN2 nucleophiles. They are negatively charged, but they're very linear and bullet shaped, right? There's not branching, and so these are excellent SN2 nucleophiles. Methyl iodide is an excellent is an excellent electrophile here. So we're going to have that attack there. And so all we ended up doing is that we added a methyl group to this alkyne. Right? That's all we did. We got this terminal alkyne, and now it's an internal alkyne. We have an additional carbon on there. So this is an excellent synthetic technique. Later, once we develop our toolkit of reactions, we have all these different reactions that we know how to do these different transformations. Then it comes time to plan syntheses. There are different techniques for adding carbon-carbon bonds. You start with a small molecule, but then you start doing Legos and you start tacking on different pieces. This is one example of a carbon-carbon bond forming technique, in addition to Grignard and Wittig and all of these other, aldol, all of these other ways of assembling a larger carbon skeleton. This is a way of taking an alkyne and tacking on more carbon content on the other side of it, a terminal alkyne, and turning it into an internal alkyne. And then you can reduce, you can remove pi bonds, you can do addition reactions, you can hydrogenate, you can do other stuff after that. It's just one thing that you can do as you're trying to build a larger molecule. So that's one reaction there. Let me see if I missed anything. Yes, Ryan, it's a nucleophilic substitution. That's correct. David, I'm not drawing with a mouse. I have a stylus pen and a tablet, so I can't. No, no, no. You as well. I am not drawing with a mouse. I have done that before when my tablet isn't working and I'm in a jam, but it's horrible. I am drawing with a stylus pen here. Okay, so 8, draw the product of the following transformation. So here we have osmium tetroxide. Osmium tetroxide. This is another flashcard here. All we have to know is that we're doing syn dihydroxylation. So you have to have your flashcard where on the front of it, you draw these reaction conditions, and on the back, you have the words syn dihydroxylation. That is memorization. And it helps when you learn the mechanisms. So for example, if you know the structure of osmium tetroxide and you look at the mechanism, it can help you remember what it is. But you don't have to memorize all of these mechanisms. All you have to memorize is these reaction conditions equal syn dihydroxylation, right? And so if you memorize that, then you just have to know what the words mean. What does dihydroxylation mean? It means we're adding 2 hydroxyls, OH and OH. Since we are adding the same group to each of the 2 carbons, there is no regiochemistry to discuss. They are not 2 different groups, so it doesn't matter which one goes to which carbon. It's the same group. So regiochemistry is not relevant. But stereochemistry is relevant, and it is syn. So we are taking 2 OHs and we're adding them to the same side of the molecule. Okay, so we just now look at the molecule that we have, and we do that. So we have our 5-membered ring, and we have the methyl. So if the OHs add to a particular side, the methyl gets pushed to the other side. So let's say the OHs add from the top. That methyl is going to get pushed down. And now we have OH and OH. And yes, we do have the enantiomer of that. Reverse the stereochemistry at each chiral center and you get the enantiomer. Because we have a flat molecule, we can have 2 OHs add on this side, or we can have 2 OHs add on this side. And they're energetically identical. So statistical dynamics dictates that if you have a large enough sample size, you're going to get 50-50, right? If you flip a coin 10 times, you might get 70-30. If you flip a coin a quintillion times, it's going to be almost exactly 50-50. That's just the nature of large numbers. So yeah, that is your syn dihydroxylation. Ryan, yeah, that's absolutely correct. A cyclic osmate ester intermediate. So the reason, right? Remember when we did hydrogenation over platinum metal, the hydrogens end up add syn because they're attached to the same solid support, right? They're coming from the same side because they're attached to a solid surface. Here it's the same. It's osmium attached to 4 oxygen atoms. So the 2 oxygen atoms are bound to the same osmium atom. So there's no way that they can add on opposite sides, right? They're being added from the same compound on the same side there. Let's see. Milo, so this is Organic Chemistry 1, which is typically taken sophomore year undergrad. I took OChem 1 and 2 as a sophomore undergrad. That's typically what happens. So that's the answer there. Okay, we got time for, let's do 2 more, maybe 3. So which set of reagents will achieve the following transformation? So sometimes you have to provide the product. Given a substrate and reaction conditions, draw the product. Sometimes, given the reaction conditions and the product, draw the substrate. Sometimes, given the substrate and the product, give the reaction conditions. So we have to understand what happened. So we had an alkyne, we had a terminal alkyne, and now in the product, we have this is called a geminal dihalide. Geminal like Gemini because they are on the same carbon there. So what happened there? Also, both of the pi bonds are gone. So we went from 2 pi bonds to 0 pi bonds. That makes me think that we did 2 addition reactions. And we might have done the same thing twice because we got a bromine on there and a bromine on there. So what what is the regiochemistry here? This is clearly Markovnikov chemistry, right? Because both of the bromines are on the more substituted secondary carbon and not on the less substituted primary carbon. So, and what did we add? We added bromine to the more substituted twice, and we added, remember, there's implied hydrogens here. There was only one implied hydrogen here. Now there are 3 implied hydrogens. So we added 2 of them, right? So the groups that we added were 2 of these, and then these 2. That's what we added. So how did we add 2 BRs and 2 H's? Well, we probably added HBr and then another HBr, right? And so how do we do that? Well, we just add HBr, right? This is if we want to do Markovnikov hydrohalogenation, it's as simple as just adding HBr, because it is a carbocation intermediate, and the carbocation is what's dictating the regiochemistry, right? We're going to get the more substituted carbocation intermediate, and then the bromide attacks that. So it goes to the more substituted, because the more substituted carbocation intermediate is a more stable intermediate. So in this case, it is carbocation stability of the intermediate that drives the Markovnikov regiospecificity. And so we clearly did, so let's just write excess, right? Excess HBr. We need at least 2 equivalents of HBr compared to the alkyne substrate, because we need to add 2 molecules of HBr to each alkyne. So excess HBr, that's it. That's all we need. Speaking of Markovnikov hydrohalogenation, we have this again. Now, this time we can go ahead and do the mechanism. So let's explicitly draw that HBr bond. Now, we have a pi bond. Remember, in any electrophilic addition reaction like this, the pi bond is acting as the nucleophile. This is a polarized bond because of the discrepancy in electronegativity between hydrogen and bromine, and then the electrons in that bond are going to leave with the bromine to make the bromide. So we get this secondary carbocation and then the bromide ion, right? Oops, sorry, I lost a carbon. Let's make sure we get that carbon on there. So we have a tertiary carbocation, and so that's what's driving the stereochemistry, right? We're not going to get the hydro. So I'll go ahead and draw in the implied hydrogen. Actually, I'll do it in pink. There's the implied hydrogen that was added, right? This hydrogen went to the less substituted carbon participating in the pi bond, so that we could get the more substituted and therefore more stable carbocation intermediate. That's what's driving the Markovnikov regiochemistry. We will not get the primary carbocation. That's not going to happen, right? So that this is stereospecific. Now, the next step is very easy, right? We have a negatively charged bromide anion, and then we have a positively charged carbocation. Well, right, minus meets plus. That's obviously what's going to happen. And then we get our alkyl bromide product. In this case, it doesn't matter which side, because we have identical methyl groups. Be aware, just as with this step, this second step is similar to like an SN1, right? We have a carbocation intermediate. That incoming nucleophile can attack from this side, or it can attack from this side. And if you are generating a chiral center, you will get a racemic mixture of stereoisomers. In this case, we are not generating a chiral center. We have 2 identical methyl groups, so there's only one product, right? We could have drawn the bromine on the wedge and the methyl on the dash. It'd be the same molecule, because guess what? This sigma bond is rotating all the time, right? And if you rotate that sigma bond, you're going to get these methyls and bromines at all the possible positions, right? So that's it. Okay, let's do one more. Oh, let me see if I missed anything. Madara, yes, I am only taking Orgo 1 questions today. In general, these are Organic Chemistry 1 office hours, so we're going to stick to Organic Chemistry 1 topics. Grim asks, will the stream be available later as a video? Yes, all of my live streams that I'm doing with Chegg as part of these office hours. If you go to my channel and you hit the live tab, you can see my live streams. There is one for every Tuesday. We're doing this every Tuesday all semester at 5 p.m. PST. So you can go back and you can see the earlier ones as well, where I did other topics. Unati says HBr plus HV light. So that's actually that's radical bromination with Br2, not HBr. That's actually you're blending hydrohalogenation and radical halogenation there. Different stuff. Let's see. Cold-blooded exotics, could you show arrow pushing? That would be this, right? These are electron pushing arrows. Electron pushing arrows always go from electron rich to electron poor, and it is very important where they initiate and end, right? Bromide, we're going from the negative charge directly to the carbon atom bearing the positive charge. Here, the pi bond, we're going from the center of the pi bond to the hydrogen that it is attacking. Students, when they first encounter electron pushing arrows, when they first start learning mechanisms, a lot of people have a lot of problems. It just takes a lot of practice. That's all it is. So we will show a lot of these mechanisms. Chiquike, what should I do flashcard for? Missed that part. So earlier when I was talking about all of these addition reactions, so like for example, this is a flashcard right here. We have to memorize on the front of the flashcard, you're putting these reaction conditions. And on the back of the flashcard, you're putting the words syn dihydroxylation. We have to memorize that these reaction conditions signify syn dihydroxylation. That you have to memorize, but that's all you have to memorize. If you know what these words mean, then you can apply them to any substrate, just the way that we saw dihydroxylation meant OH and OH, syn meant on the same side, and then we just applied that to the particular substrate. Okay, let's do one more real fast. That's it. Okay. So let's do this dibromination. So what is going to be, so how does dibromination work? Let's go ahead and do the mechanism. The pi bond will act as the nucleophile. And now it's interesting because the bromine atoms have the same electronegativity. So that's not really a polar bond. It's a non-polar bond, but it's very polarizable. Because of the size of the bromine atoms, it's a polarizable bond. So it's like it achieves a significant momentary dipole when electron excess approaches it. So the pi bond approaches it, that covalent bond begins to polarize. We get a momentary dipole and we get a partial positive on one of the bromines. So that's why that is able to happen. Students are justifiably confused by that sometimes. So let's draw the bromonium ion intermediate. This is what we end up with as the intermediate. The bromine inserts itself into that pi bond, and we end up with Br+. So that's the intermediate, the bromonium ion intermediate. And then, but we have this bromide floating around, right? We kicked off that bromide there before. So what is bromide going to attack? So this is actually like an SN2 substrate, right? We know alkyl bromides are great SN2 substrates, right? Well, this is basically that. It's just that we can have this attack. We can have this attack as though this is just a regular carbon-bromine bond. It's just that the leaving group remains tethered to the molecule because it has this other carbon-bromine bond. So let's draw what we get. Now, remember, SN2 is a backside attack. So you are going to get the trans product, right? We will not get the cis product because the bromide has to go backside attack. It has to access the LUMO of this carbon-bromine bond, which is the anti-bonding orbital 180 degrees away from the covalent bond. So it has to do a backside attack. So if this bromine, here's the plane of the molecule, this bromonium ion intermediate is pointing up like that. The bromide has to attack over here. So that'll end up on the dash, and the other one that was already on there will end up on the wedge. So you'll get this plus the enantiomer right? That is chiral actually, and we'll get the mirror image of that. And so this is called dihalogenation, and dihalogenation is an anti-addition reaction. It is anti because the two groups add to opposite sides, which tends to yield a trans product. So that's that one. Oh, yeah. Madara asks about the anti-Markovnikov hydrohalogenation. So that is a radical mechanism. It proceeds by the more stable radical intermediate, just like Markovnikov proceeds by the more stable carbocation intermediate. So I'll try to fit that mechanism in another time. If I don't get to it, check out my tutorial on anti-Markovnikov hydrohalogenation. I go over the mechanism, and it is makes it pretty clear. Oh, Ryan was in there answering as well. Yeah, so that's about it. So that's it for today. We'll pick up here next time. We'll do a few more addition reactions, and then I will start to incorporate other stuff, probably other reactions on alkene substrates like ozonolysis. I promised I would do some addition on conjugated polyunsaturated systems. We'll do some Diels-Alder, maybe some other electrocyclizations. Maybe we'll do some Wittig. We'll start to hit some of these other classes of reactions that will help us build up our toolkit of synthetic knowledge. So yeah, that's it for today. So we're doing this every Tuesday, 5 p.m. Pacific time with Chegg. This is Organic Chemistry 1 office hours. Check out that QR code if you want to see the other subjects that Chegg is offering for office hours. You can get a lot of help with all your classes this semester. And yeah, so I will see you next week, next Tuesday, 5 p.m. Pacific. See you guys next time.